From when we first could look to the sky, we've been fascinated by the heavens. The sun, along with stars visible to the naked eye, were worshipped as gods by many ancient cultures. From our perspective, the earth seemed to be at the center of creation. The sun and stars moved around us. Solar and lunar eclipses were signs from the gods. The northern lights were believed by the Romans to be caused by Aurora, the goddess of dawn, ushering in the beginning of a new day. The heliocentric model, that is, the model that correctly places our sun at the center of our solar system instead of the Earth, wasn't adopted until the Copernican revolution of the 16th century. In the following century, Kepler and Galileo further galvanized this theory, setting the stage for astronomers to find that not only was the sun at the center of our solar system, but our solar system wasn't even at the center of the universe. It wasn't until the 1920s that Edwin Hubble, using the newly built Hooker telescope and some clever math, discovered that there were a great deal of other galaxies outside our own within the universe. Continuing his observations of these other galaxies, he found that they were all moving away from us, forming the earliest evidence for an expanding universe. The Big Bang theory for the creation of the universe then came from this. If you wound the clock backwards in time to the beginning, all matter and radiation collected together into a super dense, hot mass just a few millimeters across. At about the same time, theoretical physicist Albert Einstein created a theory of relativity which gave physicists the mass that led them to make powerful predictions about the universe based on how gravity affects space-time. Our first forays into space came on April 12, 1961, when a Soviet cosmonaut by the name of Yuri Gagarin completed one full orbit of the Earth that was sent into space using a chemically propelled rocket. In July of 1969, the USA put 2 men on the surface of the Moon, marking the furthest any human being has traveled away from our home planet. Since then, we have sent numerous probes to explore the outer reaches of our solar system, the furthest of which being the Voyager 1 spacecraft. Voyager 1 was launched in 1977 and left the bounds of our solar system in August of 2013. Today, it is over 141 astronomical units, or Sun-Earth distances, from the Sun. It carries music, voice, and pictographic information about us should it come in contact with intelligent life on its journey lasting potentially tens of thousands of years. For interplanetary missions, chemical rockets could be used. One such mission may be to send a team from Earth to Mars for scientific research or to establish a colony. If we left the Earth when Mars was at its closest to us in our orbital path, a mission utilizing chemical rockets would take approximately a year to reach the planet. For interstellar missions, the use of chemical rockets just won't have the kick needed to propel us in timeframes where the original crew would survive the journey. The closest star outside our system, Proxima Centauri, is 4.2 light years away, or the distance that light travels in 4.2 years. Standard propulsion methods that utilize the action-reaction principle, or Newton's third law, can only accelerate a space vessel up to near the speed of light, as described by Einstein's theory of relativity. Relativistic effects, such as time dilation and length contraction, come into play. The onboard ship's clock may record a round-trip journey to Proxima Centauri of a few months. However, the minimum time for anyone watching on Earth would be 8 years. This best-case scenario would be short enough for this journey to be within the lifetimes of onboard astronauts. So can we accomplish this task with currently known technology? And if not, how far away would it be before we can do this? Let's look at this question by examining some of the known methods for propelling a spacecraft. Electrothermal engines create electromagnetic fields, which then create a plasma to increase the temperature of a propellant. The heat imparted to the propellant gas causes it to be fired quickly through a solid nozzle or through a contained magnetic field. Low molecular weight gases, such as hydrogen, helium, and ammonia, are suitable for this kind of system. This type of engine is used on Lockheed Martin A2100 satellites in order to maintain orbital trajectories, but it is not suitable for long-distance interstellar flight. Electromagnetic engines accelerate ions by using the Lorentz force, or by the effect of electromagnetic fields. They have the advantage of being able to apply a small force over a long period of time to accelerate a spacecraft up to 90,000 meters per second, or 90 kilometers per second. Even at this speed, the journey to Proxima Centauri would take many thousands of years. A good example of this type of engine in practical use would be the Dawn space probe. It was launched in 2007 with a mission to reach and study the protoplanets Vesta and Ceres in our solar system's asteroid belt. Without ion propulsion technologies, a single mission to both destinations would not be possible. NASA are looking at using ion propulsion technologies to send humans to Mars, which could be measured in days instead of years. We now leave behind the proven methods of spaceflight into what exists theoretically and may become a part of the technologies we use in the future to close the gap on travel times to destinations in other solar systems. A quantum vacuum thruster is a proposed engine that uses the same principles of motion to an ion engine, but uses quantum fluctuations of the zero-point field to propel it through space-time. A spacecraft with this engine would not need to carry any onboard propellant. It could theoretically continue accelerating up to significant portions of the speed of light. An RF resonant cavity thruster, or EM drive, creates thrust by bouncing microwave radiation around a cavity, which is designed to produce thrust without using the action-reaction principles of Newton's third law. It has been the subject of much criticism, as the mainstream scientific community doesn't believe that such violations of the laws for the conservation of momentum and energy are possible. And finally, the Alcubierre drive, named after Mexican theoretical physicist Miguel Alcubierre, is a spacecraft propelled by warping the space-time around it. The space in front of the vessel is compressed and the space behind expanded so as to create a sort of rippling wave through space-time that could carry its occupants to their destination faster than any light having to travel through normal space. The drive relies on the speculative idea that mass and energy density lower than vacuum could be created. Theoretically, this type of drive could propel its occupants to their interstellar destinations within days and not create relativistic effects in the process. However, the energy requirements would be enormous and are not within our current technological ability. So with current technologies, we can send humans within the reaches of our own solar system within their lifetimes, but not to destinations light years away. It is difficult to say when and if the next generation of technologies needed to discuss to other solar systems will exist, as we still don't have a complete theory of everything in physics. Such a theory would be able to unify relativity and quantum mechanics into a larger picture of the universe. This should then provide us with the understanding needed to create and build vehicles capable of escaping our home in the universe and give them the capability to jet off into the unknown reaches of space and time.